Okay. Anybody have any homework questions? Yes. On what are we on? Math. Oh yeah. Okay. Um, so it says ddt of 2xt squared, quantity 2xt squared, is equal to 50. Come on. Where when t is equal to 1, x is equal to 5. All right, so the first thought you probably have is just to take this derivative and work from there. So we have two functions of time. We know x is a function of time, and t squared is a function of time. So you have to use the product rule for that derivative. So you get 2x times x dot times t squared. Not 2x. That's add deriving. Okay, so 2x dot times t squared plus 2x times 2t, so 4xt. And then that's equal to 50. So now, is there a way to solve that by separation of variables? No, because if you add negative 4xt to both sides, you have x's and t's mixed together, you can't divide them out there, and so you're stuck. So instead, notice that this is a really easy problem. dz dt is equal to 50. That's a super easy separation of variables problem. And so instead of working from this and trying to solve immediately for x of t, we're going to make the substitution that all this stuff in here that we're taking the derivative of is a new variable. We're going to, now we're going to have to re-express this boundary condition in terms of this new variable. And once we figure out z of t, then we can solve because all of this is equal to z of t. Okay, so what we're going to do is we're going to say z is a function of time is equal to 2xt squared. That's a function of time because x is a function of time and t squared is obviously a function of time. And that boundary condition now says that when t is equal to 1, x is equal to 5. So x of 1 is equal to 5 now becomes, so we're going to choose a value, we're going to choose the value of t to be 1 and the value of x to be 5, and we get that, so 2 times 5 times 1 squared is equal to 10. And so that says that when t is equal to 1, z is equal to 10. So z of 1 is equal to 10. Everybody follow why I did that? So now we have a boundary condition for z instead of for x. And now we have everything that we need to, so this is our new boundary condition. Thanks. Okay, and now the differential equation is this. Well, I'll rewrite it. So dz dt is equal to 50. And this is our new differential equation. And then once we figure out z of t, then we just have to do the algebra to re-express it as x. So this says that dz is equal to 50 dt. Integrate both of those, and you get z is equal to 50t plus c. And then use the boundary condition that says when t is equal to 1, z is equal to 10. So 10 is equal to 50 times 1 plus c. So c is equal to negative 40. And so our function z of t is equal to 50t minus 40. So that answers a question, but not the question that we were asked for. So now we have to figure out what x of t is. And so we have 50t minus 40 is equal to, the substitution we made was z is equal to 2xt squared. And so 2x is equal to 50t to the minus 1 minus 40t to the minus 2. And so x as a function of time is equal to 25t to the minus 1 minus 20, minus 20t to the minus 2. Any questions about that? So you have to choose that sort of intermediate dependent variable, solve for that, and then calculate x after. You got a question back there? The last solution? Well, so we know this is z. And then we go back to the definition of z. When I introduce z in the first place, z is equal to 2xt squared. So I set this function, this is z, and I set that equal to what it's defined as 2xt squared. And then I just did the algebra to separate x. Was there another question? Yeah.
When you define that z, is it a function of both x and t, or just?
It's only a function of t because x is also a function of t. You know. So yeah, all you have to do is just remember that whenever x comes up, it's also a function of t. So when you take its derivative, you need a chain rule term. Any other questions? Yes. Any other questions on that one? Okay. 8 and 11. Okay. Okay, so number 8. So we have 5t squared x double dot is equal to 50. And our two boundary conditions are x of 1 is equal to 2, and x of 10 is equal to 20. And I think, so this is a second order ordinary differential equation. And the example of one of these that I did in class had one boundary condition for x and then one boundary condition for x dot. This has two boundary conditions for x. That's fine though. The way we're going to do this is we're going to, so if you have one boundary condition for x dot, then you do separation of variables once, come up with an expression for x dot, and then you use the x dot boundary condition to find your constant of integration, and then you do the next step. We can't do it like that here because we don't have a boundary condition for x dot. So what we have to do is separation of variables once to get x dot, and it'll have a constant of integration. Then do it again, even though we don't know that constant of integration, and we'll have an expression for x that has two constants of integration in it. And then once we have that, we can plug both of these in, and we'll get a system of two equations for two variables to solve. Okay, so that's the way you have to do it. Anytime you have your two boundary conditions both in a second order differential equation, when they're both on the dependent variable itself, the function itself, and neither of them is on the derivative. So x double dot is equal to 50 t to the minus second. And x double dot I'm going to write as dx dot dt. And now separation of variables. So you get dx dot is equal to 50 t to the minus second dt. Yep. Thank you. So I divided both sides by the 5 also. So this 50 should be a 10 now. And now I can integrate both sides. What do you get when you integrate dx dot? X dot, yep. And over here, we have negative 10t to the negative 1 plus c. That's the combined constant of integration for both sides. I'll call this C1 because we're going to have to do it again, and we can't solve for that yet. We don't have a boundary condition that lets us solve for x dot. So now I'll do it again. We have dx dt is equal to negative 10t to the minus 1 plus c1. Multiply both sides by dt, and we get dx is equal to negative 10t to the minus 1 plus c1 dt, and we can integrate both sides of that. And we get x is equal to negative 10 natural log of t plus c1t plus c2. Okay, and now we need to use both of those two boundary conditions with this equation to find those two constants of integration. The first boundary condition says, so boundary condition 1 says x when time is equal to 1 is equal to 2. And so plug that into this equation and you get 2 is equal to negative 10 natural log of 1 plus 1 times c1 plus c2. That goes away. and you come up with your first equation in this system that says C1 plus C2 is equal to 2. Call that equation star. And then boundary condition 2 says x t equals 10 is equal to 20. So again, go back to this equation, this solution for x, where we just don't know the constants yet. And you get the 20 is equal to negative 10 times the natural log of 10 plus 10c1 plus c2. And we can write this as 10c1 plus c2 is equal to, what's 20 plus 10 natural log of 10? 43.03. And I'll call that equation 2 star. And now equation star and equation 2 star are two equations for two variables. Those two variables are C1 and C2. And solve that however you want. And once you have C1 and C2, plug those into your function for x of time, and you have the complete solution. Any questions about that one? Okay, so anytime you have, I'm gonna wait for Jason to, he's concentrating super hard. So anytime your boundary conditions for a second order differential equation, or let's say any higher order differential equation than first, anytime they're given in terms of the dependent variable itself, and there aren't any of the derivatives, you're going to have to solve a system of equations like that for the constants of integration. Okay, number 11. So we have this function u, this vector u is equal to xy squared. And we want to come up with an expression for, so what's u dot in terms of x, y, x dot, and y dot. So this is just a, you have to use product rule and chain rule for this. So the idea is x is equal to x of t and y is equal to y of t. Otherwise, those time derivatives wouldn't make any sense. So I guess that's kind of the giveaway that we need to think about. So for the taking the time derivative of the x component, we have a product of two functions of t. And so it's going to be derivative of the first times the second plus the first times derivative of the second. And that's it for the x component. And then for the y component, we have two things going on. y squared is a function of y, and y is a function of time. So the product rule says we have derivative of the first times the second plus the first times the derivative of the second. And for now, I'm going to write that like this. No, y squared. And the reason I'm taking this intermediate step is that we have to remember that now we have to use the chain rule on this because this is a function inside a function. So the top is still x dot y plus xy dot. The bottom is x dot y squared plus x times, so now you can think of this as, this needs to be x times dy squared dy times dy dt. That's what the chain rule says. So what's dy squared dy? The derivative of y squared with respect to y is 2y. So 2, I'm just pulling the 2 out to the front, x, y, and then dy dt is y dot. Bless you. Any questions about that one? Any other homework questions? Yeah. Okay. All right, so this is a system of differential equations. So t squared x dot x is equal to 10. And the boundary condition corresponding to that one is that time is equal to 1, x is equal to 0. And then the second equation says y dot is equal to cosine t. And the boundary condition for that one says when time is equal to 1, y is equal to 15. For a system of differential equations, what matters to us is that they're uncoupled. So we wouldn't be able to do this if there were y's in this equation or x's in this equation. Since all the dependent variables stay in their own equation, we can just solve them as two separate things. So it's really two different problems. So let's see. We have x dot x is equal to 10 t to the minus second. And I'll rewrite that as dx dt times x is equal to 10 t to the minus second. And multiply dt to both sides. You get x dx is equal to 10 t to the minus second dt. And you can integrate that. The integral of x with respect to x is x squared over 2. And that's equal to negative 10 t to the minus 1 plus c. The boundary condition says when time is equal to 1, x is equal to 0. So we have 0 squared over 2 is equal to negative 10 plus c. And so c is equal to 10. And so x squared over 2 is equal to negative 10 t to the minus 1 plus 10. And now we'd like to express x as a function of time. So multiply both sides by 2, and we get x squared is equal to negative 20 t to the minus 1 plus 20. And then take the square root of both sides, and you get x is equal to square root of negative t to the minus 1 plus 20. And let's see. Then you have to think a little bit about what happens with the plus and minus and whatever. So what's going on here? So when t is, so where does this become imaginary? When if t is less than, if t is less than 1 or greater than negative 1, this is imaginary, right? So our boundary condition is for time equal to 1. So this is the solution. Well, I guess it only goes imaginary. It doesn't, it's still, are there any cases where, let's see. Okay, so this is just plus or minus, and you can have imaginary answers. Hopefully, you know, in this class, we're not ever going to deal with answers that are imaginary. So there would be a restriction on the domain that just said it has to be great, you know, t has to be greater than 1 or less than negative 1, right? Less than, just greater than 1. You're right. Time is always going to be positive, yeah. And so I guess so whatever. It would be imaginary from 0 when time is anywhere from 0 to 1, and then it would be real after that. But that's the answer. And then the second one, so this one looks easier. dy dt is equal to cosine of t. So dy is equal to cosine of t dt, and you can integrate both sides. And you get y is equal to sine of t plus c. Then the boundary condition for that one says when time is equal to 1, y is equal to 15. So 15 equals sine of 1 plus c. C is equal to 15 minus sine of 1. So I didn't say anything, and I don't think we've done a problem yet where we've had to determine whether we're in radians or degrees. What do you think is going on with this? You probably in physics 1, it wasn't, you didn't dwell on that a lot, but there's a correct answer for this. It has to be in radians, and the reason for that is whenever you're taking a derivative of a trigonometric function, because of the way the chain rule works, you have to be in radians. So can someone tell me what 15 minus sine of 1 radian is? $14 point something? You just do the decimal. Just kidding. That's not really possible. 0.15? 65? Sorry. 14.16. Okay. Okay, so y is a function of time is equal to sine of t plus 14.16. Any questions about that one? Any other homework questions? So now we're done with those mathematical preliminaries. And the first topic we're going to get into is particle statics, not statics, particle dynamics. Well, actually, before we get into dynamics, we're going to get into particle kinematics. Who remembers the difference between kinematics and kinetics? It's a super nuisance that those names are so similar. So kinematics is the one that's just describing motion. It's not dealing with any causes of the motion. So we're not talking about forces or energy or mass yet. A longer word, but the similar topic. So kinematics is just describing motion without its causes. So we're not talking about force, mass, or energy. And then when we get into kinetics, that's the shorter word, more complicated topic. And that includes all of kinematics, but now it combines the causes too. So it combines the kinematics with causes of motion. One way to think of kinematics is it's every kind of calculation that you could do exclusively from watching a careful video. Okay, so without being able to measure the mass, without being able to measure forces and stuff like that, if you were watching a video of something moving around on a grid and you had a stopwatch, you could do all the kinematic calculations. You could figure out the position as a function of time and figure out accelerations and all that stuff. But kinetics, you couldn't do anything to figure out forces. And what's a particle? So what you need to remember about a particle is not an actual thing. It's a mathematical treatment of things. So it's a mathematical treatment of an object. A particle does have mass, but has no length dimensions. Or orientation. And so it's not just a matter of size, whether something, something little is a particle and something big isn't a particle. It really has to do with what you want to calculate. If you need to know an object's orientation, or you need to know what's happening on different sides of it, then you can't treat it as a particle. If all you care about is the motion of the center of mass, then you can treat it as a particle. So like, for example, when people do dynamics of like the motion of planets and stuff, those are obviously ginormous things, you know, not not the kind of thing that you would tend to think of as a particle, but you do particle calculations because you don't care whether it's turned this way or turned that way. You just want to know where in space it's going to be at what time. So the position vector um, is another way of saying and to think of it as a vector, if this is your coordinate system and this is the object, position vector is just a vector with its tail at the origin and its head at the object. Then the velocity vector is the time derivative of the position, and the acceleration vector is the time derivative of the velocity, and that means that it's the second time derivative of the position. And if you don't remember anything else from this class beside this, you get an F. But still, this is the most important thing. So notice, don't think like velocity is the derivative of the position. Same thing with acceleration. It has to be velocity is the derivative of position with respect to time. Okay, and if you're given the velocity as a function of something other than time, that would make it a lot easier to take the derivative with respect to that other thing. That doesn't change the definition of velocity, So velocity is the derivative of position with respect to time. So if you have a function like velocity is a function of the z position, okay, and that could definitely happen, and we'll actually see problems like that. You can't say, so it would be really easy to just take the derivative of that and say that the acceleration is dv dz, but that's just not what acceleration is. Okay, so there's two directions you can go with these functions. You can be given, okay, so 2 directions you can go with these relationships. The first one is going from position to velocity and or velocity to acceleration. And if you're going in that direction, the function itself is all you need. So a function of time is all you need. If you're going the other direction, so if you're going from acceleration to velocity and or velocity to position, then you're going to be using separation of variables. And that means that you need a boundary condition for each step along that path. So what you need is a boundary condition for each component at each step along the path. Okay, so let's say that we're given velocity as a function of time. And let's say that, so we're doing a two-dimensional problem, and let's say this is equal to 2t, the x component, negative t for the y component. So first, what's the position vector as a function of time? We don't need any more information than this because we're just taking a derivative. P is just equal to the time derivative of v. And so, nope, I'm going the wrong way. Dang it. Scribble that out. This should be acceleration. Okay, so to calculate the acceleration as a function of time, acceleration is just the time derivative of the velocity. And so that's equal to 2, negative 1. And we didn't need any boundary conditions or anything. But now for part B, if we want to know what the position vector is, we have to be given enough boundary conditions. How many do we need in this case? We're taking one step, and we have two components, so we need a total of 2 boundary conditions, one for x and one for y. So let's say that we're given that the x component of position at time equals 0 is 5, and the y component of position at time equals 0 is 0. Okay, well, this is a vector. You can think of that as a system of equations. So I'm going to solve this as a system of equations that says, so we know that v is equal to 2t negative t. And so I'm going to rewrite that as px dot is equal to 2t and py dot is equal to negative t. And then these are the boundary conditions that go along with it. And so to do the first one, separation of variables says dpx dt is equal to 2t. So dpx is equal to 2t dt. You know, maybe I should have just called these, I'll leave it like this, but I could have just as easily called these instead of px and py, I could have just called them x and y. And then it would have, you know, it wouldn't have looked as messy, but it would be the same problem. And so px is equal to t squared plus c1. And now we'll use the boundary condition that says when time is equal to 0, px is equal to 5. So 5 is equal to 0 squared plus c1. So c1 is equal to 5. So px as a function of time is equal to t squared plus 5. And now I'll go to the y equation. It says dpy dt is equal to negative t. So dpy is equal to negative t dt. Integrate both of those. And you get that ty is equal to negative t squared over 2 plus a constant of integration, c2. The boundary condition for this one says when time is equal to 0, py is equal to 0. So 0 is equal to 0 squared over 2 plus c2. So c2 is equal to 0. And that says that py as a function of time is equal to negative t squared over 2 plus 0. And now finally we can put these two together. And our final answer is that the position vector as a function of time is equal to t squared plus 5 for the x component and t squared over 2 for the y component. Any questions about that? Yes, thank you. I shouldn't try to remember stuff. Good Friday.